Hello viewers, welcome once again back to my channel, Math Made Easy with PDY. In today's lesson, we are actually going to look at the topic Plane Geometry 2. So under Plane Geometry 2, we are going to learn about Circle Theory. I also call it the angular properties of circles. Come along with me whilst we go through the circle theorems. But what are you expected to know under circle theorem? By the end of the lesson, you should be able to 1. Draw the circles and name the various parts. 2. You should be able to state and verify at least 3 circle theorems and use it to solve problems. Someone may ask, what then is a circle? A circle is a set of points at a fixed distance from the center. In other words, you can also say that a circle is a locus of points equidistant from a given point known as the center. Again, a circle is a locus of points equidistant from a given point known as the center. Now let's look at some of the parts of a circle. The first part we'll be considering is the radius. The radius. Now the radius is simply a line segment drawn from the fixed point known as the center to touch the circumference of a given circle. The plural form of radius is radii. The plural form of radius is radii. We also have another word which is the circumference. The circumference is simply the perimeter of the circle. In other words, the total distance round the circle is known as the circumference. And any section of the circumference is known as an arc. Any section of the circumference is known as an arc. Another term we'll be using in our discussion is a chord. And someone may ask, what then is a chord? A chord is a line dividing a circle into 2 parts. A line drawn to divide a circle into 2 parts is a chord. Now, when you draw a line that divides a circle into 2 equal parts, then that line becomes a diameter. So we say a diameter is a chord. In other words, I always say it's a special chord which passes through the center. It is a special chord which passes through the center of the circle. That is what we know as the diameter. Or you can also say that a diameter divides a circle into 2 equal parts, as I said early on. Now, its length is twice that of the radius. We'll be talking much about this into details when we start our lessons on mensuration. So, twice the radius gives us the diameter. Moving forward, if a chord is not a diameter, the 2 resulting unequal regions of the circle are segments. The minor segment is the smaller section and the major segment is the larger section. I'll be showing you diagrams to all these terms very soon. Then we also have a sector. A sector is a region of a circle bounded by 2 radii. A sector is a region of the circle bounded by 2 radii. The smaller one is a minor sector and the larger one is the major sector. Then the last term we'll be coming across in our lessons on circle theorem is a tangent. A tangent is a line drawn touching a circle at a given point. In other words, I always say that it's a line drawn in space touching a curve or a circle at a given point. These are some of the terms you'll be coming across in our discussion with circle theory. So as we looked at the various terms of parts of the circle, this is the diagram to the parts of the circle. So we actually looked at a radius, which we said is a line segment drawn from the center of the circle to meet any point on the circumference of the circle. So that is the radius. Then we have the fixed point, for which you have set of points round it and they are equidistant to it. That is known as the center. And then we said we also have the circumference of the circle, which simply refers to the total distance round the circle. And a section of the circumference is known as the arc, or part of the circumference is known as the arc. Then we also talked about a chord. A chord is a line drawn to partition a circle into two segments. And we said that we have the minor segment and we have the major segment. In the situation whereby, or in the case whereby the chord is not passing through the center of the circle. So we also looked at a diameter, and we said that a diameter is a special chord that is drawn to pass through the center of the circle. Then we talked about the tangent. We said it's a line drawn in space to touch the circumference of a circle at a given point. We also discussed the sector and then the segment. The sector is a bounded region found in a circle when two radii bounded with an arc is formed. We have two sectors formed. We have the minor sector, which is a smaller region, and then we have the major sector, which is a wider region. Then we have the segment. It's also an area bounded by a chord and an arc. That is, so we have this region here as a minor segment, and all the section here is a major segment. Likewise, we have the minor sector here, and the other is the major sector. So without wasting my time, let's go straight to the circle theory. Now we are beginning with 1, which states that the angle subtended at the center of the circle is double the angle subtended at the circumference of the circle, which means that when you have any angle at the center of a circle, twice the angle at the circumference gives you the angle at the center of the circle. Now, there's a condition attached to this theorem. The condition is that they must all subtend on common points, 2 common points, meaning the angle subtended at the center should be on the same set of points for which the angle at the circumference are also subtending on. So please be careful with this theorem. Now, I make it very easy for students to understand this theorem by calling or giving it the name the arrow theory. The arrow theory. That's a very simple way to remember that. The arrow theory. So when you have any angle subtended at the center of a circle and another angle subtended also at the circumference of the circle, twice of whatever angle you have at the circumference of the circle will give you the angle at the center of the circle. We are going to verify this angular property very soon. So with the help of the GeoGebra, let's verify the first theorem we are actually looking at, which is twice the angle at the circumference of the circle equals the angle at the center of the circle. Now, with this GeoGebra software, I have my circle drawn, and on the circle, I have 3 points, point A, B, and C. Now, and the center of the circle has been labeled O. Therefore, I've measured angle ACB, and I've also measured the angle at the center, which is angle AOB. Now, if you look at angle ACB, which has been given as alpha, which is equal to 39.73 degrees, and when we consider this angle to angle AOB, which is an angle labeled beta in the diagram, then it means that it's having a value of 79.46. Then when you multiply the angle alpha by 2, you are getting the angle beta, which is 79.46 degrees. Now, as I said, another name I give to this theorem is the arrow theorem. If you look at it carefully, you realize that it looks like an arrow, a pointed arrow. Now, if I even shift the point C, if I shift the point C closer and closer to any point on the circumference of the circle, you realize that the value alpha remains unchanged. It's the same. It doesn't change. And as I said, it doesn't matter that you have the shape formed in this order. It is always going to be the same. So this verifies that twice the angle at the circumference of the circle gives you the angle at the center, on condition that they all subtend from the same point or the same chord. From the same point or the same chord. Now I'm bringing on board another term, which is what? A chord. Because I can draw a line segment from A to meet B, so that the diagram resurfaces to become a new shape altogether. But when we verify the angle property, it doesn't change. It's the same thing. So maybe tomorrow you may see it as 2 points. Today you'll be seeing it as a chord. So please take note of that. Please kindly take note of that. There's another property we are going to verify very soon. Now, if it should happen that, let's say, the angle ACB does not find itself within the same segment, what happens to the angle of C? Let's verify that. So let me do away with the chord AB, and then let's verify that angular property there. So when I do away with the chord AB, now let me shift the angle C, moving from one segment and bringing it to another segment. So bringing it to another segment, you realize that the angle alpha has changed. The angle alpha has changed, all because they are not finding themselves within the same segment. It has traveled from the major segment into the minor segment. So the angle alpha has changed. Please take note of that. So this angle property, there are conditions attached to them, and be careful with these conditions. Now, let us also verify whilst I increase out the point B. Let's see what will happen. So kindly look at the angle alpha and the angle beta. So let me just open up the point B a little, and then let's see the outcome of the result. So you realize that alpha, at the current location of point B, alpha reads an angle of 59.19 degrees, whilst angle beta reads an angle of 118.37 degrees, which simply tells you that when you multiply 59.19 by 2, you are going to get 118.37 degrees. I believe you are following what exactly I'm doing. As I said, we are looking at the circle theorems and then verifying them so that we can easily remember and use them as such whenever we have any question to answer. Because remember, any question given to you under circle theorem is not drawn to scale. Therefore, you need to understand the concept and then use it to answer questions when necessary. You can equally do this verification using your constructional tools, that is the mathematical set. You can just draw a circle and then come up with the necessary angles, and then drawing to scale, you measure them and you can verify them as well. So since we've been able to use the Geogebra software to verify the angle properties connecting angles at the center of the circle and that of the circumference, then we are moving on to the next angular property. The next angular property we want to look at is angles subtending by the same chord are equal. Angles subtended by the same chord are equal. Remember, we are talking of angles, so we mean more angles. So angles subtended by the same chord, they are equal. I have a similar diagram here. If I have a chord AB, this chord AB has partitioned the whole circle into two segments. We have the major segment and the minor segment here. So if I form any angle on the circumference of the circle within the major segment, each of the angles formed subtending on the same chord or the same points, they are said to be equal. So we say angle APB, which is labeled alpha, is equal to angle AQB for the fact that they subtend on the same chord or the same points. I'm using the word points for the fact that maybe tomorrow you might not see the chord. It might just be missing, and therefore you only see A and B there. Still, that property holds. Likewise, when I come into the minor segment, you realize that we have angle ARB. R is a point on the circumference of the circle, and it makes an angle beta. And therefore, angle ARB equals angle ASB. And that has also been labeled beta. And we say that these two angles are equal. So again, angles subtended by the same chord, they are equal. You can rephrase it and say that angles subtended by the same chord within the same segments, they are equal. Now let's use our Geogebra board to verify this angular property. Here we are on our Geogebra board. Now we have a given circle with center O, and it has a chord AB in short dashes. Now we also have the major segment, which we found up here, and then we have the minor segment. The minor segment doesn't have any angle there. We'll be drawing it, and then we'll take the measurement, and then we'll conclude on that. So considering angle ACB, which is found within the blue lines, now we have it labeled alpha. So alpha is giving us an angle of 62.39 degrees. Then when we verify angle ADB, that is also giving us angle beta. Now, looking at beta equal to 62.39 degrees, then it means that is the same as the alpha value here. So the angle D at the circumference of the circle is the same as the angle C, on condition that they are subtending on the same chord and they meet at the circumference of the circle. Please take note of that. They meet at the circumference of the circle. Now, let's verify something. What if they did not subtend or they did not meet at the circumference of the circle? What then would that angle be? But before we do that, let's assume that if I should have shifted the point D from its current location, and let's verify the angle beta. Do you observe that it changes or not? Now, when you look at it carefully, you realize that the angle beta remains unchanged. It's the same. So I can even put it directly on C and realize that it matches it perfectly, that the angle beta and the angle alpha, they are the same. They are the same. And there's a condition attached to it, because they all subtend from the same chord or from the same point A and B, and they find themselves within the same segment. Now, I was asking this question: what if this angle D and C are not subtending at the circumference of the circle and not subtending on the same chord? Now, let's take it that we have another point. Let me bring in another point. Let me place a point here, the point E. And then let me join E. Let me join E to A with a line segment. Then from E also to B with another line segment. Now, let's verify something. So let's measure angle A. We are measuring angle A, E, and then B. Now, when you measure angle AEB, it's giving us gamma. Let me try and move the gamma sign. So gamma is reading 71.81 degrees. It's reading 71.84 degrees, which is totally different from the 62.39 degrees. So it tells you that gamma, the point E, as long as it has not subtend on the chord at the circumference of the circle, that is why we are getting a different value. So let's see. Assuming I move the point E, I move it very close to the circumference of the circle, you realize I get closer and closer to the value we are supposed to find. So now that we are getting close, you realize that it is what? 62 point. So it's getting closer to the actual values for angle beta and angle alpha, which are points exactly on the circumference of the circle. So please remember that with the angles subtending on common chord or common point, they must be on the circumference of the circle before those angle properties will hold. Please take note of that. Now let's move on into the minor segment, and then let's look at the angle property also there. So I'm selecting some 2 points there. One point is here, that is F. Another point is also here, that is G. So let's create our angle. So from A to F and from B to F. Now let's measure angle A. Let's measure angle AF. Let me take it from the other side. So let's measure angle B, F, and A. When you measure angle B, F, and A, you are getting 117.61 degrees. 117.61 degrees. It is not the same as the angle alpha nor the angle beta. Now let us also measure the other angle G. So let's join A, G, and then B, so that we can also measure angle B, G, and then A. When we measure angle BG and A, that is equally given as 117.61. 117.61. So that is delta and that is epsilon. So delta and epsilon are recording the same values, all because they are angles subtending within the same segment on the same chord. So you can choose to shift the point F very close and close to G. The value delta and the value epsilon will never change. So this actually verifies that the angle property holds. Now, let me come up with a very simple name that may help you remember this theorem easily. Now, let me do away with the point E. When I do away with the point E, let us analyze the shape of the angle formed within the major segment. You realize that it looks like a bow tie. I don't know. The guys will confirm that it looks like a bow tie. Likewise, the angle here too also looks like a bow tie. Yes. These days we have some new designs for bow ties. So I always call this theorem, for easy remembrance, the bow theorem. The bow theorem or the bow tie theorem, so that you can remember that. But remember, this theorem states that angles subtending on a common chord or common points within the same segment at the circumference of the circle, they are equal. So now that we've been able to verify the bow theorem, now let's move on to the next theorem. Now, with respect to the next theorem, then we are looking at the angle at the circumference subtended by a diameter is a right angle. Or more simply, we can say that the angle in a semicircle is a right angle. So in other words, what you can say is that when you have any angle formed at the circumference of the circle meeting a diameter, automatically that angle is 90 degrees, irrespective of wherever this angle is drawn or how big or small the angle be. But remember that any angle subtending on a diameter at the circumference of the circle, automatically it is a right angle. So let's verify this property using our Geogebra board. So to verify that, we have our circle drawn with center O and the diameter is point A and B. Now, in this case, I have an angle C formed at the circumference of the circle, and you realize that this angle is actually subtending on the diameter. Now, I can move the point C from its current location to any other position on the circumference of the circle, and you realize that it's still giving me an angle of 90 degrees, which is the angle alpha shown in the diagram. It doesn't change. Perhaps you may think that I've fixed it, so let's verify by drawing another point and taking the measurement for that angle. So we have another point placed D, which is in another segment. Let me join A to D with a chord. So we have from A to D and then from D to B with a chord. And therefore, let me measure angle B, D, and A. Straight ahead, you can see that it's showing the angle beta. And the angle beta measures an angle of 90 degrees. Likewise, I can shift the point D very close and close to B, and it's still 90 degrees. So please take note of that. Any angle that subtends on a diameter at the circumference of the circle, it gives you a right angle. It gives you a right angle. So for easy remembrance, we can say that this is known as the semicircle theory. The semicircle theory. I believe, viewers, you are following whatever I'm explaining into details. I'll make another video showing you the calculation means of proving all this. Now let's move on to the next theorem, which is actually the cyclic quadrilateral theorem. The cyclic quadrilateral theorem. Now someone may ask, what then is a cyclic quadrilateral? Now it is one that can be inscribed in a circle. In other words, one whose vertices lie on the circle's circumference. So if you have any circle drawn and you have a quadrilateral drawn in it, for which all the vertices of the quadrilateral has been drawn to touch the circumference of a circle, then we say that the shape gives you a cyclic quadrilateral. A cyclic quadrilateral. Now, what angular property do we need to know when it comes to cyclic quadrilateral? The opposite angles of a cyclic quadrilateral add up to 180 degrees. So for instance, in this diagram here, we have angle alpha, angle delta, angle gamma, and angle beta. Now, angle alpha and gamma are directly opposite to each other. Therefore, we say that when you put these two values together, it should be giving you a total angle of 180 degrees. Likewise, when you add up beta and delta, you must get an angle of 180 degrees on condition that the whole shape gives you a cyclic quadrilateral. So let's verify that one also our software. So in verifying our cyclic quadrilateral theorem, now we have our circle drawn with center O, and it has 4 vertices on the circumference of the circle, which is points A, D, C, and B. Now I've joined each of the points with a chord, and therefore we have some angles measured in there. So you realize that angle BAD gives us alpha, which is 91.5 degrees. Likewise, angle ADC gives us angle delta, which is 74.4 degrees. Angle DCB actually also gives us gamma, which is an angle of 88.5 degrees. And finally, we have angle CBA, which is angle beta, which gives you a value of 105.6 degrees. You can use your calculator to add up the angles there directly opposite to each other, and you realize that 91.5 plus 88.5 degrees will give us a total angle of 180 degrees. 180 degrees. Likewise, you add up 105.6 degrees to 74.4 degrees. You equally have an angle of 180 degrees. You can shift D from wherever it is to a different location. You realize that the angle D does not change. It's the same value, 74.4 degrees. And the value of B does not change. But you realize that that of gamma and alpha, they were changing. But even though they did change, you had gamma being 117 degrees and that of alpha being 63 degrees. So they are directly opposite to each other. Hence, it still gives you a total angle of 180 degrees. So the angular property of cyclic quadrilaterals actually holds, that the sum of the opposite interior angles of a cyclic quadrilateral gives you a total angle of 180 degrees. I believe it is well understood. So I can choose to increase the size of the circle. It's still going to be the same. Thanks so much, viewers, for joining the call and also for joining my lesson. I'm so privileged to be explaining mathematics to you in a very simple way. Kindly do your best to support my channel, Math Made Easy with PDY, so that more videos can be made for better understanding of mathematics. Remember, if you've not subscribed, kindly hit on the subscription button and then also hit on the notification bell so that you may be one of the first persons to get notified when any video is actually uploaded. Kindly do well to like and share the video so that we can reach out to many people who find mathematics to be difficult. Remember, math is very simple. Thanks so much again, and God bless you.